Good afternoon. My name is Christos Giagkoulovits, and I'm with the MST group led by Professor David Cumming at the University of Glasgow. And today I will give a presentation about the hybrid amperometric and potentiometric CMOS system. So the lecture will be as follows. First, I will talk about the implementation of potentiometry in CMOS, and then how we use these how we use these I'm really sorry. Concepts to build the CMOS ISFET array. The same will be done about the implementation of amperometry in CMOS and how we implemented this on an amperometric microelectrode array. And then the concept of using both of these technologies to make a hybrid CMOS chip, combining both of them. Then I will go on to explain a feasibility study that we conducted to prove that this is possible. And that's how the presentation is going to be concluded. So first, potentiometry in CMOS. Potentiometry is used for pH meters with the use of glass electrodes. And the way this is miniaturized in CMOS is by the use of a MOSFET with an extended gate up to the top metal layer that senses hydrogen ions, sensing their charges that actually modulate the channel of the device now called an ISFET. The way that we implemented this in an array format was using a four transistor pixel architecture, and the ISFET was implemented by a PMOS in a common drain topology. We have 256 by 256 array of ISFETs, and 64 of these are read at a sampling period. The chip was fabricated in a standard CMOS process, and tantalum pentoxide was deposited over the active area to enhance the sensitivity. Thus, we achieved a sensitivity of 45 millivolts per pH. And as you can see on the graph, we achieved a linear pH response from pH 2 up to pH 12. Now, the next section is about amperometry. Amperometry is done by the use of electrodes, and it's monitoring reduction and oxidation reactions. And the current is measured to see these reactions effect. A potentiostat is used to accurately set at which potentials these reactions happen. The way this is implemented in CMOS is again by the use of a top metal layer, whereas this time the passivation layer on the top is etched, and we deposit stack of metals to have an inert metal layer that constructs a microelectrode. This is gold in this case, and we chose this as because it is an inert metal and it cannot be corroded by the chemical environment. The use of microelectrodes has an advantage over their large-scale counterparts because they enhance the sensitivity as they have a large current density, meaning that there's a smaller current, though the density is quite large. And the implementation on CMOS is actually improving the signal-to-noise ratio as the electrodes are in close proximity to the current readout electronics. Using these principles, we implemented a CMOS Amperometric microelectrode array in the same CMOS process. And we designed a 16 by 16 microelectrode array of working electrodes. Working electrodes are the transduction elements in these systems where the current is actually measured. And we have designed it to have 16 integrated potentiostats to drive the array, thus achieving 16 different cyclic voltammograms. And the cyclic voltammogram is actually been using the technique of cyclic voltammetry, which is scanning the potentials to find a redox peak, a reduction or oxidation peak, or both, where the reaction is happening, and this is recorded as a current. The concept is to integrate both of these technologies on a single platform to make a hybrid electroanalytical CMOS chip. And if this is performed, we can achieve complex chemical measurements and have an insight at the molecular level in the microscale. It can also be used to make both techniques measurements in conjunction and measure substances that are sensitive to either one of the techniques. In this part of the lecture, I'm going to talk about the feasibility study that we implemented on the ISFET array. In order to integrate both technologies, we deposited some gold electrodes on top of the ISFET array, which were operated by an external potentiostat to read the current. And the arrangement induced the ions inside the solution to arrange themselves over the area of the ISFETs, and their charge was recorded with the ISFET acquisition system. As a first step, we patterned some these microelectrodes photolithographically on a silicon nitride chip, a dummy silicon nitride die, and we implemented cyclic voltammetry, which is actually scanning the potentials. As you can see, this is the input signal. And the resulting cyclic voltammograms are shown here, where we can see the reduction and oxidation peaks, which is about 400 millivolts, which is the redox potential of ferrocene, the analyte that we used. And the last graph is showing a time-resolved cyclic voltammogram. It's the same measurement. And also, you'll see later why we did it time-resolved. The same process was conducted on top of the CMOS ISFET array. And in order to insulate the bond wires and the bond pads from the chemical environment, we had to use a chemically resistant epoxy to encapsulate them, as well as a polypropylene ring to make for a container. The results are, the combined measurement results are here. As you can see, this is the same kind of graph with the time-resolved measurements, and it follows the same response as the silicon nitride deposited microelectrodes. The input current that was applied is the same, has the same potential range, and the potential was recorded at the vicinity of the working electrode at a line of ISFETs that were, and these measurements were averaged. So the potential is actually, it's following the input potential. As you can see, it's inverted. The reason why it's inverted is because the input potential is the potential of the working electrode versus the reference electrode, whereas in this case, it's not in regard to the working electrode. That's why it's inverted. And it is following the same response. At the reaction peaks, you can see that there is some influence on the potential characteristics of the modulation of ions around the working electrode. And this potential characteristic is showing us the modulation of the ions arranged in the diffusion layer around the working electrode, giving us an insight into these effects. There is a difference. The potential range is compressed. It's, as you can see, compared to the input voltages, and that's because of the ISFET response to the recording the potential. So an amperometric and potentiometric measurement was proven that it can be conducted by this feasibility study. And the future step is to use both of our technologies, integrate them on the same CMOS platform, and perform and miniaturize these measurements in the microscale, and give us a better insight into the reactions, the amperometric reactions. Many applications are possible by this technique. One of them is an integrated version of scanning electrochemical potential microscopy, a scanning probe microscopy technique developed by Alan Bard. Whereas in this case, we'll have it integrated in the microscale level, and we're going to skip the scanning part, as this is an array of sensors. And I would like to thank my group, the Microsystem Technology Group, and all the staff from the James Watt Nanofabrication Center, as well as Professor Leroy Cronin and Christoph Busche from the Chemistry Department at the University of Glasgow. Thank you very much.